Hello and a warm welcome. This is lab number 20, titled Interference and Diffraction Through a Vertical Slit. With this lab, we are continuing our exploration of an important phenomenon of light, so-called diffraction. This is a phenomenon that can be explained only if you're looking at the light as a wave. It is a phenomenon that occurs when the light bends around very small objects or through very small apertures. In this case, we are going to be looking at a straight small opening of a very small width that's on the order of scale of a wavelength of light. This distinct phenomenon that's known as a diffraction can be explained using so-called Huygens principle, where we are looking at a light as a set of multiple waves that are interfering with each other, creating a distinct type of interference consisting of bright and dark spots that are a result of either a constructive or destructive type of interference. In the case of a vertical slit, the diffraction pattern is going to also be very distinct. It is going to consist of alternating bright and dark spots along the straight horizontal line. It turns out that the distance between the two neighboring bright spots that are separated by a dark spot can be calculated and is a function of the wavelength of light as well as the distance between the diffracting object and the back screen on which we are observing this distinct diffraction pattern. So as a goal for this lab, we are going to continue discussing the theory of a diffraction as well as setting up an experiment in which we are going to observe the diffraction phenomenon, or specifically diffraction pattern created by the vertical slit. We are going to perform the measurements as well as the calculations in which we are going to calculate the distance between the two neighboring maxima in the diffraction pattern and then also compare our measurement to the theory.
In this lab we are going to use the following equipment: a red laser diode module, a laser holder, a vertical slit with a width of 0.1 millimeter, a lens holder to be used to hold the vertical slit, and then for the measurements we are going to use the measuring tape, a protractor, a pencil, and a large white sheet of paper. To observe the diffraction pattern to the vertical slit, we have mounted our red laser diode module onto the laser holder, taped it and pointed in the direction of the back screen. We have also taped the tape ruler, and here in the front of the aperture of the laser we have positioned our index card with a vertical slit, and we have pointed the laser directly to that vertical slit, and as you can see in the back on the screen we are producing a specific diffraction pattern that is characteristic for the vertical slit. So in order to proceed with this lab, we are going to dim the light in the room and then perform the corresponding measurements. As it can be observed on the back screen, we have a very distinct diffraction pattern that's been created by the vertical slit. This diffraction pattern is in a horizontal direction and consists of the whole bunch of maxima and minima. So we have a very strong light or maximum right at the center, followed by a dark spot, and then the bright spot and the dark spot and the bright spot, etc., both on the right hand side and on the left hand side. So the task in this lab is to observe this distinct diffraction pattern created through the vertical slit, and then also to mark all these maxima and minima on the back screen and then conduct specific types of measurements. So in addition to making the sketch on the back screen of our very distinct diffraction pattern created through the vertical slit, we also want to record the distance from the index card with the vertical slit all the way to the back screen. So we have positioned the measuring tape, and the measuring tape has been positioned at 0 for the aperture for the vertical slit, and if you go over to the other side we can see that the back screen has been positioned at about 120 centimeters. So that's going to be our distance between the aperture, vertical slit aperture, and the back screen. Okay, so here's our improved diffraction pattern that we received by diffracting the laser beam through the vertical slit. As you can see here, our diffraction pattern is along the horizontal line, consists of a whole bunch of maxima, and in between we have the minima. So I have a first bright spot or first maximum here at the center, and then here's the second bright spot, third bright spot, and fourth bright spot on the right hand side, and then over on the other side we also have the second, third, and fourth bright spot. In between, we have the minima that we are interested in, and those are the minima that we are going to measure. So we are going to estimate the center of the first minima, which is going to be this one here, and then also center of the first bright spot. So this here is going to be our first position of our first minima, y1. And then continued, here is going to be our second minima. It's going to be our second minimum, y2. And then finally here we have third minimum. It's going to be labeled as y3. So let's now measure these three minima, these three distances of the three first minima. So here we are measuring about, looks like it is going to be 7 millimeters. So our y1 is 7 millimeters. Position of the second minimum is about, here's 10, around 16 millimeters. And then finally the position of the third minimum is about 25 millimeters, y3 equal to 25 millimeters. Let us now determine the predicted value for the width of the slit used in our experiment. We are going to do three calculations for three dark spots in our diffraction pattern. So the values that we are going to use for the wavelength is lambda equal to 650 nanometers for our red laser diode module. We also know the distance from the diffraction slit all the way to the back screen. We measured that to be 120 centimeters. Now for the first order dark spot in our diffraction pattern for m equal to 1, if you use the formulas given on the right, we come up with the following formula for the width of the slit. Lambda times L over y1 here we can substitute for lambda 650 nanometers times the L, which is 120 centimeters over the y1, which represents the distance of the first dark spot in our diffraction pattern from the center of the diffraction pattern. In our case, it was 7 millimeters, so we are going to put 7 millimeters here. Now what you can do here, you can convert everything to the base units. So we're going to have 650 times 10 to the negative 9. And then 120 centimeters is equal to 1.2 meters over 7 millimeters being 0.007. And then we can perform the math here using our calculator. So we have 650 times 1.2 over 0.007 and then times 10 to the negative 9, which is this. So we get 0.00011 meter, or we can convert this immediately to millimeters. So this is going to be equal to 0.11 millimeters. Let's do the similar calculation for the second order dark spot. So for m equal to 2, we also have the formula on the right from which we can extract b. So b is going to be equal to 2 times lambda L over y2, and then we are going to substitute specific values, and then we are going to convert these values here immediately into the base units. So we have 2 times 650 nanometers, which is equal to 650 times 10 to the negative 9 meters, multiplied by L, which is 120 centimeters or 1.2 meters, and finally y2, we measured it to be 16 millimeters, which is equal to 0.016 meters. And again, here we're going to use our calculator. So in this case, we have 2 times 650 times 1.2 over 0.016, and then multiplied by 10 to the negative 9, gives us this value, and this is the value in meters so that we can convert into millimeters. So we would move the decimal point 3 places to the right. So here we are gaining the value of 0.0975 or 0.98 millimeters for the width of our slit. And then finally the third calculation for the third order dark spot. We have again formula on the right, 3 times lambda times L over y3. Again, we are going to substitute and convert into the base unit immediately. So we have 3 times 650 times 10 to the negative 9 times 1.2 over y3, which we measured to be 25 millimeters or 0.025 meters. Then we're gonna again call our calculator into help here. 3 times 650 times 1.2 over 0.025, and then times 10 to the negative 9 is this value. So this is the value in meters. To convert into millimeters, we're going to move decimal point 3 places. So this is going to turn out to be 0.094 millimeters. Now these 3 values for the B, we can average them to come up with an average for the width of our slit. So we have the B1 and then B2 and then B3, and our average B is going to be equal to B1 plus B2 plus B3 over the 3, or 0.11 plus 0.098 plus 0.094 over 3. Again, using calculator, we have 0.11 plus 0.098 plus 0.094 over 3 gives us a value of 0.1007 millimeters. So this is our calculated value for the B based on our measurement. Now we also know that B is supposed to be, so B nominal is supposed to be 0.1 millimeter. So what we can do here, we can calculate the percentage error. So in our case, the percentage error would simply be equal to the absolute value of the B calculated minus B nominal over B nominal times 100, which in our case is going to be 0.1007 minus 0.1 nominal over 0.1 nominal times 100. So if we do this math, we're gonna get 0.1007 minus 0.1 over 0.1 times 100 gives us the percentage error of only 0.7%. So we can make a conclusion that our measurement was very valid and resulted in a very small percentage error compared to the nominal value of the width for the vertical slit.